Essential Java. We're looking here at our kind of roadmap. As I said, that our roadmap is going to span the first few weeks, certainly, and it'll be introduced to other topics. So we're not just doing Java for the next 3 weeks, but we're doing the left-hand column today, which is overview, classes, and then control statements. So we've done our introduction. You can see roughly where Java came from. And the basic syntax of the language we've been looking at for the last few minutes, which Siobhan gives you an idea how familiar really it is with many common programming languages. And you spent quite a bit of time now looking in detail at the basics, how we declare variables, the kind of operators that are appropriate for variables of different types, the distinction between primitive and reference types, and then reference types in particular, how we create those, what it means to perform assignments on those, and then some very tricky areas around what if the reference variables are not initialized. We'll be returning to that in some detail later on. The mission now, though, for the next 20 minutes or so is to look at the classes in particular, and more specifically, how do we design and implement a class syntactically, and what are the primary features of a class once we have called it into existence. So classes, they go back a long time. First class introduced in a language called Simula in the late 60s. This was a language aimed at simulation, as the name suggests. And the classes were used to represent real-world entities under simulation in that context. The notion of a class as this type of entity was picked up very strongly by Smalltalk in the 70s and directly led to its inclusion in C++ and then onto Java. And of course, it's proliferated to many of the standard canonical languages these days. So we'll look at what a class is in Java, how it's defined, how it's associated with specific files and compiled entities, how they're packaged together, what a jar file is, and then also how we break down a class into fields, methods, and constructors. Classes have very specific fields and methods that are defined static, which we need to look at. And then we also need to look at some widely used methods that are present in all classes, which is something we will need to be grappling with as we proceed. So this is what a class looks like. It's straightforward enough, really. We have the keyword class. We have the name we're inventing, usually capitalized, and we have the visibility of the class. And for our purposes, we'll largely be running with public classes. This means they are visible outside the package in which they're defined and also outside the class file itself. We store classes in a file. We would name the file to match precisely the class name. So if we choose to call a class policy, then the name of the file must also be policy, and that includes the case of the name being consistent. If we step outside this, then we'd expect our IDE and Eclipse would be monitoring that and letting us know we're not quite adhering to the rules. Classes are contained in packages, and the package must be declared usually at the very top of the file containing the class. And of course, the same package can contain multiple classes. So the same package statement here can appear on a dozen classes, and all those classes will be considered to be part of the same package itself. Naming packages is often done with reverse DNS to ensure some attempt at universality, but any name is viable. You don't have to use dots. And when we import a class, that is when we include it into another class, we must specifically identify what package the class comes from. In the first example here, we are declaring, creating an object of a specific type, and we're fully identifying the package name succeeded by the class name as we create the object. But in the second example, we're choosing something much more easy to work with. We're just using the class name, because we will have imported the class explicitly early on in the same file. Again, this is an innovation over C++'s include mechanism. Its modules are supported directly in the language itself, and the syntax of the language is able to check that we're pulling in the packages correctly. We'll largely prefer the latter approach, except when we have the potential for ambiguity, in which case the former would be used. That's very rare. Back to our Javadoc output, you can see on the left here, we're able to distinguish between packages, which are visible in the given library we're looking at, and then individual classes within packages. So any class we're identifying here is in the context of the package selected in the packages list. Back to our diagram again. Our compiler is generally compiling one file at a time, and each file becomes one generated .class file. So we go from .java to .class via the compiler. Class file is binary, it's machine independent, and it's in a machine code designed to target the virtual machine on which Java runs, the JVM. We can see this in Eclipse if we reveal the navigator as well as the explorer view. On the left here we have a logical view, which is the one you would have seen from last week's labs. You can see the three classes we had and also the library we're using. On the right, we're looking at a physical view, which can be revealed if you do show view navigator. And here we can see there's not one source folder. There's a source folder, a lib folder, and a bin folder. And the bin folder is where the generated classes are generated by the compiler. So these classes one-to-one mapping to our package structure. In fact, the JVM only needs the class files to execute. It doesn't need the original source. Part of the machinery for achieving this is the JVM, the compiler rather, is looking for an environment variable called class path. These class paths then are used by both the compiler and the runtime to decide what class files can be loaded, where they're loaded from. So as class objects and classes are encountered at runtime, the machine code variants are loaded. This is highly dynamic, and it can be a complex issue, but generally we'd expect our tooling systems to manage this for us now. You may though have seen in our lab last week, you had to interfere in the build process by manually adding a library to your class path. And this was done via the GUI in our Eclipse environment. We had to download the Xstream component we were experimenting with, and it had to be added to the build path explicitly. Otherwise, we weren't able to gain access to the classes in the jar file at either compile time or runtime. Okay, some terminologies then that we will be familiar with as we proceed into the course: the class name and fields. Fields are central to the memory of the class, or to memory footprint. They are the state that objects that adhere to the class will be maintaining. Here is how they look as we define them in the source. The class policy has 3 fields: client, policy number, and premium, and the types are declared as if they were variables. And they are in fact variables, we call them instance variables. We have an additional qualifier here, the access modifier, which indicates how available the field is external to the class. Private would mean completely unavailable. Same rules apply for just conventional variables as Siobhan is exploring. If we don't initialize them, we expect them to be initialized to 0 for numerics or false for Boolean, or we can choose to initialize them ourselves directly as we would for variables inside a function. In this instance here, we're initializing a string to a given constant value, and here we're using another class, and this other class is the of a different type to the class we're in. We're creating a client object inside a policy object using the new syntax Siobhan was discussing. Okay, so it's reasonably logical how it's laid out. The constructors also play a role in initialization, and they may be used to either augment or perhaps even replace the type of initialization I'm showing you here. And I'll look at constructors shortly. There are rules around these accessors. We've just discussed the private modifier, but there are, of course, two others. We have protected, and we also have public. When we discuss inheritance next week, we'll get a better handle on what protected means. Public, in effect, means the fields are completely exposed and visible. For the classes we'll be developing, we largely make the fields private and the members public. But that's just our convention for the moment. If we don't specify any visibility qualifier, then it's considered to be default. Default is not really a keyword in this context, and its visibility is slightly different from the other two. Largely means that classes and fields are accessible, members are accessible within a given package. Okay, we'll come back to this a little bit again shortly, but if we're trying to visualize the nature of an object and methods and their role, then it's useful to think in terms of methods delivering behavior and fields retaining state. So if we had a class object and it's a class construct representing a bicycle, for instance, then the bike in motion may have certain attributes like its current speed, RPMs of the machinery, what gear we're in. The behavior, though, which we control this state, we would visualize as methods, changing a gear, braking, or changing the cadence. In Java, all instances of class have the same methods. That is, the same methods run and are adhered to all objects. When we send a message to an object, we're executing that method. However, we're executing that method on whatever object we send the message to. Let's take a look at a more extended example. Again, you've seen this in Siobhan's exploration a bit earlier. Policy class may have fields, client, premium, policy number, and then it has a range of methods. In this case, they're simple enough methods to retrieve or access the private fields. This is how it looks. Policy class as defined, and then we're specifying methods inside the class with their own access modifiers, return types, method name, and parameters. The constructor is a special method used in object creation only. It's named to match exactly the class name. It doesn't have a return type. It may have parameters. And it has a conventional body which can contain any initialization or algorithm we choose. In this example here, we're choosing to invoke other methods in the same class in the constructor. These constructors are triggered by the new statement, as you've seen. And here is a constructor that takes several parameters. We're passing a client object, a string, and a double. And we are storing those values directly in the object itself via the setters we've already defined. And at the end of the screen here, we're showing the creation of a policy object itself. New means it's created. It's created on the heap. It's garbage collected by default, as we discussed. And while we're creating the object, we're also creating a secondary object, client, which is passed into the constructor. And we have two literals then we're initializing the object with. Okay, there's a more complete example of the same class showing you general structure and particular indentation style. Now, moving on, still within the context of the classes we're exploring, we're looking at the specific qualifiers we can introduce that aren't visibility qualifiers, but are scoping qualifiers around the range and lifetime of specific fields and methods. And this is the static method, static qualifier. Here we've got a visualization here of perhaps a class bouncing ball and 3 objects, 1, 2, and 3, ball 1, 2, and 3, each one having their own position. If it's in a game and if we've got a physics engine, we may choose a specific gravity value for the entire game. And that gravity value may be expected to be enforced for all bouncing balls in the given simulation. We could have each ball possessing its own gravity value, but we choose instead to have one gravity which is shared by each of these objects. And in Java, this is made incarnate by the static keyword used when we're defining the field. So our incantation now is starting to look a little bit more lengthy. Public final static int. We're saying we've got a field called 1. It's an int. There is a shared version of this across all count objects. It will never be modified. That's what final means. And it's accessible externally. Public. Because it's accessible externally and because it's independent of any object, we can access it via the class name. You can see that in action here. We're using, because the capital C is used, we're using the class name dot field name. And this is quite valid because it's public and we're printing it out. We're doing exactly the same thing down here. We are accessing an info field, which is static, public, but we're accessing it via not the class, but an object of type count. And we have a choice of doing this, one or the other, direct or indirect. Largely, we'd expect our style guide to give us advice on this, and the style guides will probably lean towards always using direct access, as it's more obvious what's occurring. Also possible to have static methods. In this instance, we have a static method that's retrieving a field. Field info is private in this instance. And we can access this method directly or indirectly, as we've been discussing. Indirectly means we're reaching from an instance of the object. Directly means because it's static, we can access it via the class name. And again, I'll point out the class name we're using here, count, is capitalized. So we're seeing clearly a different access mode. Static fields then move on to some other widely used methods in Java classes, and particularly where they reside and how we access them. Java implements a feature sometimes called a cosmic object. This is the notion that there is one class from which all classes are derived, even if you didn't explicitly make that decision in your class itself. Now, we haven't really discussed how inheritance works yet, and we'll be looking at that in a week or so. But there is this class object, which is at the root of all classes in the environment. This is a feature that differentiates Java from C++. C++, very similar syntactically to Java, but it does not have the concept of a global object. That notion actually comes from Smalltalk, which introduced the concept in the late 70s. So this class object, it's up there as the base class of all classes, implicitly defined. And this base class has a range of methods already defined for us and already implemented. Now, the number of methods is very small. This is the complete list, I think. So it's not like it's a substantial range of capabilities. And often we're interested in interfering or re-implementing a small number of these methods. In particular, we're interested in looking at the toString method and the equals method, which would be considered to be fairly important methods in how our class works. We also would probably need to keep an eye on the hashcode method. The remaining methods, some of them are largely disused now and are like junk DNA in terms of how Java has evolved. Others are specifically associated with multi-threaded behavior, which we will not be covering. Here's the equals method. You'll notice in this code fragment, we've got an override directive, and we'll discuss that in next week's class. The equals method's job is to compare any object with another object and return true or false. Are they equal or not? This implementation can be a little bit complicated, showing you a simplified version here. And in this version, we are looking at just seeing if the other object is a book. If it is a book, then we proceed through this rather complicated looking expression to turn the other object into a book and then reach into it to see, do the two strings match if a string is used for the ISBN. This is a little bit beyond where we're at for the moment in Java, so we'll be looking again at equals in a week or two. Hash code is another one. This is again a implementation already in the base class object, and in general, if we are putting our objects into collections and the collections are mapped in some way, that is, they are part of some key map collection, then we are very interested in the hash code and how it behaves, and we may need to implement hash code ourselves. This usually doesn't mean implementing our own hashing algorithm, but rather delegating to a hash code that might be part of one of our members. One interesting aspect of strings, which we've seen already but haven't really looked at in any detail, is that they are immutable. That is, when you create a string, you can't really change it after the fact. This may seem a little bit surprising, because very often we are doing modifications on strings as part of our business logic. Here's some examples of creating strings. But every time we do an operation here, we are generating often new strings from the old strings. So when I call, for instance, to uppercase here on hello, I'm not converting hello to uppercase. I'm generating a new string, which is a copy of the old one that is uppercase. If we do want to do surgery on a string, then we're looking at string buffer as opposed to string. And string buffer has some range of features to allow us to modify in place the characters of a string. You can see delete, replace, and so on down there. String manipulation is considered a little bit awkward in Java compared to other languages like Python or even JavaScript, and not one of its strong points. We've seen println occurring once or twice there in the earlier examples. Println is accessed via system.out, and this is part of the standard library. When we say system, we're reaching into an object that contains some standard features associated with the environment in which the process is running. When we say out, we're accessing a public static member of that object. So out is public static final stream, effectively. And finally, when we say println, we're just calling a method, and then we're passing parameters on that method when we pass the string in this instance. Okay, that's a quick tour through classes and how they're structured. In general, the labs really are where you'll get to grips with the structures and the concepts we're giving you guidance on here in considerably more detail, and they'll make it concrete. We're just looking at our clock here now, and we had planned to go through control statements, but I think it's probably the case that I will step through control statements, or rather flick through them very quickly, And we'll get on to object-oriented concepts because I certainly want to give Siobhan about 20 minutes to discuss your assignment. So I'll skip over control statements very quickly. I won't hand you back to Siobhan, and I'll spend a little bit longer time on object-oriented concepts, which is our final topic. Control statements, they're very similar to many other programming languages. So there is nothing really particularly new or groundbreaking in the way Java has modeled control statements. Various control statements you see here, if then else, switch, for, while, do while, they're all very familiar from the languages that Java derived from. So they're all almost identical to how these control statements work in C and in C++. And indeed, you'll find them very similar to the way JavaScript, also C#, also Go, and also Kotlin also behave. If statements, standard structure, some examples here. We can see we've got Boolean condition to be tested, and then the true or the false part. It doesn't matter how you use your braces in the if statements. Particularly, you may choose to have omit them for single statements or include them if the branches have multiple statements. In general, we would look towards style guides as to which would be preferable, and most style guides would suggest that this is the preferable style, even if you only have one statement on either part. Nested statements, need to be careful here. Generally, the old rule, an else belongs to the nearest elseless if. I think I remember from my college days. I think that still holds true 30 years later. Some more examples of nested statements. Switch statement is directly derived from C. It's a jump table, effectively. It's a little bit old-fashioned now, and you'll see successor languages, particularly Groovy and Kotlin and Swift, have innovated and improved the structure of this quite significantly. Here's some more examples. The gotcha with the switch statement is the break is needed. And if you leave out the break, then you get a fall through where possibly all branches can be invoked. Again, that's not Java's fault, that's C, and that's almost goes back to original assembly language that C tried to supplement it. Okay, the loop statements are for, again, this is almost universal now in most programming languages. You can see the basic structure here, you should be used to it. And the strange notation here is how we would introduce an infinite loop in an expression. And the while loop, again, while loops are quite straightforward and identical to as they would be in C and C++. Do while loop ensures one iteration at least before determining how many iterations should take place. Okay, that's a very quick whistle stop of control statements. I don't plan to do any more on that really, and it's something you can look at yourself in your own time if you want a refresher. Okay, I'll conclude before I hand back to Siobhan and discussion on the assignment with just a brief review of some of the terms we've already seen today. And these are the object-oriented concepts we've been encountering, particularly this diagram. We talked about methods and behaviors. I think, Dan, you liked that example. We think of object state being the memory of an object and being retained by the fields, and these fields are sometimes called instance variables. We then regard the methods as an expression of the behavior of the object, and these methods can be invoked or triggered on the object by sending a message to it. We aim to have objects that are loosely coupled. That is, the bindings between objects are fairly clear and obey specific rules around the relationship between the classes and the packages in which the classes are embedded. It's very easy for us to evolve a very complex set of relationships that would be difficult and challenging to maintain. And we'll be looking at how that can occur and some principles for avoiding that a little bit later on. You will see in the OO world diagrams like this. This is a sequence diagram showing you what might be happening in a given scenario if several objects were interacting. Broker, policy, person, object interacting in this instance. And we're seeing here a swim lane or timeline of an object. And in this context, we're looking at how methods are invoked. And then if methods are interacting with other objects, how we can model that visually. These diagrams now are often automatically generated as opposed to hand-drawn, and we might do a little bit of experiments on that later on in the course. In those diagrams, we talk about a message sender and a receiver. The receiver is the object that is being invoked using the message that the sender is choosing to dispatch. Again, we've seen examples of this in the code fragments you've looked at to date. This is how we might visualize what's happening over a given time sequence. Now, one last few phrases that we'll be encountering again. The notion of considering the public methods of a class to be its protocol, or rather its public protocol. That is, if we have access to an object and we want to interact with it and use it, we can only use the methods that are made visible to us. If there are private methods or protected methods, they are not available and we can't invoke them. So Java, being strongly typed, adheres fairly strictly to this rule. It means that the compiler is able to police exactly what you're doing with an object and prohibit you from going beyond the scope or protocol of a given object. In fact, that very much characterizes the static, strongly typed nature of Java. If you're working in JavaScript, of course, those bonds are completely unleashed. Fields, as we mentioned, are often private, sometimes known as instance variables. They're the state of the object. They are the object's memory, and they retain in the fields specific values associated with a given point in time in the execution. Encapsulation is a principle. It's often called implementation or data hiding. Principle whereby our classes retain privately access to the fields, which means they're only exposed via public accessors. Common pattern in Java, perhaps a bit less emphasized in other languages. And then this coupling and cohesion notion. This requires careful consideration as we evolve our classes into form a system to perform some function. If the classes are all coupled across packages and extensively between each other, then our design is said to be very high in coupling and perhaps also low in cohesion. If we can reduce the number of dependencies and where we have dependencies, retain them within the context of a module, then we talk about higher cohesion and lower coupling. And there's strong guidance to show us that the overall stability, lifetime, and maintenance burden of systems is considerably alleviated by going for high cohesion and low coupling. These principles predate object-oriented thinking, and they've been taken into considerable detail and comprehensiveness since object-oriented arrived. Another notion of classes, we could consider them to be factories for creating objects. We could regard them as a template for creating objects of the same size, same type. Depending on the language you're dealing with, then these terms may be in use or may be used in associated literature. If we're talking about instances, then every instance is the same. It's a boilerplate generated by the class's constructor. I have a class called person and I create two person objects. Then I'm looking at those two objects identically structured, but of course their fields contain different values. We may also say that those two objects though have the same or support the same protocol. That is, we can interact or trigger their behavior using exactly the same signatures. Now, inheritance is something we've mentioned once or twice, the context of this cosmic global object class we all inherit from. But of course, there's specific inheritance, which we need to discover in a bit more detail in the next session. The policy class we've been exploring here may be a base class for customized or what we call specialized policy classes, home, auto, and life. And we would use the terms generalization and specialization in this context. Home policy is generalized by the policy. The life policy is a specialization of the policy class. Now, inheritance is a somewhat controversial topic, and we will be devoting some time to it in the future. It could be used for reuse. It could be used because it represents some real-world concept. I hope you like that one, Dan. Bicycle, mountain bike, and road bike and tandem are bicycles, so we can model them directly in our class constructs. However, inheritance is a subtle topic, and there's more than one type of inheritance. And in fact, we will be drawing your attention to good inheritance practice and what is now considered to be bad practice. And we'll discuss those in some detail in a future class. Polymorphism is a central building block to object-oriented thinking, and it relies on a variety of inheritance. It could either be good or bad. We'd hope it would be good when we make use of it. It centers around the idea that when we're sending a message to an object, that is, when we're invoking a method in an object, we may not know exactly which method is to be triggered, because there may be more than one. If we're using inheritance, and if we define a dog and a cat as derived from animal, we have three methods here called talk. And when we invoke talk on an object, we may not be quite sure as we invoke talk which one we're getting. This is through the magic of overriding and inheritance, and it's a central feature of the language and how it works. It draws from the dynamic binding capability of the language. Dynamic binding being, again, a key feature of object-oriented languages in general. And if I have access to an object reference animal and I invoke talk, then I am calling a method, but I'm not quite certain which method is invoked. That'll depend on how I am dynamically bound at that point. Again, we'll see that in action in the labs, I think, rather than abstractly here. Okay, take a short break now, and Siobhan is going to introduce you to the assignment then. Don't worry about the brevity of our introduction. Your assignment is several weeks away, and we can come back and revisit it in subsequent weeks. The assignment specification, as I mentioned at the start, is not in our current topic, but is up here in our assignments area. And just before Siobhan gets into it, and before we have our little break, our labs are very much designed around preparing you for this assignment. So our next few weeks' labs are a bit different from last week. Last week was just experiment, probing some features. The next few weeks will be building up the baseline for your assignment, which you will be invited to complete. Okay, I'll take a little break now, and then we'll be back. Siobhan will be back with you shortly. I won't see you again until next week. Okay, see you in a few minutes.